Hello everyone, welcome to this advanced lecture on mixture model by Center for Computational Technology CC Pune. This particular lecture is part of the advanced lecture series on multi-phase flow modeling using the commercial software Fluent. In this lecture, we will study in detail the mixture model, which is a type of multi-phase flow model available within Fluent. Before beginning this lecture, let us have an overview of the topics that we are going to study in this particular lecture. First, we will have the necessary basics of mixture model. This will give us an overview of the fundamentals and basic concepts related to the mixture model. Then we will see the applicability of mixture model, which are the problems or situations where we apply the mixture model. Then we will see some of the limitations of the mixture model. After that, we will see the user inputs that are required in order to activate and set up the mixture model within Fluent. In the later part of the lecture, we will have a brief overview of cavitation effects and how we can model them using the mixture model. Also, we will see how we can model the compressible flow effects using the mixture model. We will end the lecture with summary and references. So let us begin this particular lecture, which is focused on the mixture multiphase model within Fluent. In the first slide, we will see basic concepts of the mixture model. The mixture model is basically a simplified version of the Eulerian multiphase model. The mixture model solves the momentum equation, the continuum equation, and energy equation for the mixture. The volume fraction equations are solved for the secondary phases. Algebraic expressions are solved for relative velocities. For turbulent flow, a single set of turbulent transport equation is solved for the mixture phase. The mixture model does not consider particle-wall interaction, and it also does not consider particle-particle interaction. Now let us see where do we apply the mixture model. In the earlier slide, we said that mixture model is basically a simplified form of Eulerian model. So the first question that comes to our mind is, which problems do I use the Eulerian model and which problems do I use the mixture model? There might be a slight confusion while using the mixture model because it is basically a Eulerian model. There are three criteria on which we can take a decision as to whether we use the mixture model instead of the Eulerian model. First is the dispersed phase distribution. If there is wide distribution of dispersed phase, we prefer to use the mixture model. That is, we have particles which vary in size and the largest particle do not separate from the primary flow field. In such cases, mixture model can be used. If we have dispersed phase which is concentrated just in portion of the domain, and if we have a narrow distribution of the dispersed phase, we go for the Eulerian model. Next criteria is the drag laws between the different phases that we are modeling. If we exactly know the drag law, it is always good to go for the Eulerian model because it will give accurate results. But if we are not sure about which drag laws are applicable to our system, instead of investing computational effort into a detailed Eulerian model, we can use the mixture model. Next criteria is the computational effort and the time. If we have a simpler problem and we require a quick solution, it is always recommended to go for a mixture model because it is computationally less costly. That is, it requires less computational time. But if we require a highly accurate solution and we know all the details of the drag laws, then it is always recommended to use the Eulerian model because it will give more accurate results, but it will also consume more computational effort. So these are the basic three criteria based on which you can make a decision whether to go for a simplified mixture model instead of using the detailed Eulerian model. Mixture model also comes with its limitations. We will discuss them one by one in this particular slide. The mixture model is not available with the density-based solver. Only one phase of the mixture model can be defined as a compressible ideal gas. We cannot model solidification and melting in conjunction with the mixture model. We cannot model solidification and melting along with mixture model. The single et al. Cavitation model is not compatible with LES model of turbulence when we use the mixture model. That is, when we activate the mixture model, we cannot use the single et al. Cavitation model together with the LES turbulence model. The mixture model cannot be used for solving inviscid flows. The shell conduction model for heat transfer for walls cannot be used along with mixture model. When we are tracking particles in parallel, we cannot use DPM model with mixture model if shared memory option is enabled. So these are some of the limitations. Some of the basic limitations like the density based solver cannot be used and only one phase can be defined as compressible ideal gas, while rest are solver related limitations, that is we cannot use some submodels with some other submodels by using the mixture model, etc. So these are the limitations that you have to keep in mind while using the mixture model. Now let us begin our next section, that is user inputs that are required for mixture model. In this section, we will study all the user inputs that are required in order to set up the mixture model, all the parameters that we have to fill up in different panels, and all the solver settings that we have to ensure in order to solve a problem using the mixture model. First, we will see how to define a primary phase. Primary phase in case of mixture model is defined in the same manner as the Eulerian or any other multi-phase model. We go to problem setup, then click on phases, then we click on the phase 1, which is the primary phase. After this, the primary phase panel opens up. We set the name of the primary phase, then we select the material of that phase. If we need to edit that material, we click on edit, then the edit material panel pops up. We can change all the properties of the material of that phase in this edit material panel. Once we have done this, we click on OK and our primary phase is defined. Next is secondary phase. Now the secondary phase in the mixture model can be non-granular or it can be granular. First we will see how to set up the non-granular phase. We select the secondary phase in the phases list. This can be done by going to problem setup, then clicking on phases, then we click on secondary phase and click on edit. Next, the secondary phase panel pops up. We enter the phase name here. There are two options, granular and interfacial area concentration, but when we are defining non-granular secondary phase, we do not select any of these. So our secondary phase is non-granular in nature. Next we select the material for the phase, which can be selected here. We can also edit this material by clicking on edit, and various properties of that material can be edited. As I just mentioned, we can edit or define the material properties by clicking on edit here. Then we define the diameter for the bubbles or droplets of particles of this secondary non-granular phase. This diameter can be set here. So this is how we define a secondary phase which is non-granular in nature. Next is we define granular secondary phase. We select the phase from the phase list. That is, we go to problem setup, we click on phases and we select the secondary phase. Then we click on edit. Then we enter the name of the phase. Then the secondary phase panel pops up. We enter the name of the phase here, and since our secondary phase is granular in nature, we click on granular. Once we click on granular, various granular properties will open up here in this dialog box. We select the material here. We can also edit the material properties by clicking on edit. Then we enable granular option. Then we continue to give further properties for the granular option. In this slide, we will see how to set up the properties for the granular secondary phase. Within the secondary phase panel, we activate the granular option in order to indicate that the secondary phase is granular. The first property that we have to give after setting up the phase material is diameter. This is the diameter of the granular particles. Granular viscosity is the second property. This is the kinetic part of the granular viscosity of particles. Granular temperature must be specified here in this particular dialog box. This is the temperature for solid phase. This is proportional to the kinetic energy of the random motion of the particles. As we have already studied the granular model in our Eulerian lecture, these terms are the same corresponding term for the granular model. Solid's pressure can also be specified. This is the pressure gradient term in the granular phase momentum equation. This is to be specified here. The next property is the elasticity modulus, which is to be specified here. This is defined by this particular term, which is given by G. Then we need to specify the packing limit, which is specified here. This is the maximum volume fraction for the granular phase. Next, we will see how to activate the interfacial area concentration option and what are the properties required in order to set up this interfacial area concentration. First, we select the phase, which is the secondary phase, and click Edit. Then the secondary phase panel pops up. Here, below the granular option, we activate the interfacial area concentration. We enter the name of the phase here. Then we select the material for that particular phase. We can define or edit the material properties. Then we activate the interfacial area concentration option, which is given here. We have to make sure that the granular option is disabled, otherwise the interfacial area option will not be visible. Let us now see how do we define drag between phases. For mixture multiphase flows, drag exists between phases, that is, we can define the interaction between phases in terms of drag force. We have to specify the drag function, which can be given within the phase interaction panel. Within the problem setup phases, we click on interaction. Then the phase interaction panel will pop up, and in that the first tab is the drag. Here the pair of phases for which we are going to define drag appears, that is, we are currently defining the drag coefficient between phase 2 and phase 1. Various options for defining drag are available here. We can use the Schiller-Norman for spherical particles. We can also use this Morse-Alexander option or model. This is very close to Schiller-Norman. We can also use the symmetric option for very high secondary phase volume fraction. That is, if the secondary phase volume fraction is closer to 1, we use the symmetric option. Now let us see how we can modify the slip velocity definitions. Slip velocities between phases can be solved during mixture calculations. These definitions can also be modified. For this, we go to phases and click on interaction. Then the phase interaction panel will pop up and we have a tab called slip in which we can define the configurations or models for calculating slip velocities. Currently, we are defining a slip velocity configuration or model between phase 2 and 1. Various options are available here. We have the Mannion et al., which is used as default. This is the algebraic slip method which is invented by Mannion et al. We can define none, which means the secondary phase has the same velocity as the primary phase, that is, there is no slip velocity, or we can use a user-defined function also. So 3 options are available for us in order to set up the slip velocities.